Hi everyone. So today we're going to look at an example of AC circuit analysis, and if you're confused by all the theory we did so far, hopefully it should come together when we do this example. So here is a question. We have a source, a transmission line, which we represent by inductive reactance and a resistance, and we have some load details, and the load details here are that it is a 50 kilowatt load at 0.8 power factor lag, and the voltage across the load is 440 volts. Now notice we specify the voltage at the load side and not the source side, because typically that is what you want to do. You want to ensure the voltage at the load remains constant. So if you think about TN Tech, you have to be supplied at 115 volts. TN Tech can't just generate a voltage at their generator and say, well, whatever you get at your home, it doesn't matter to them. So this would be the format of most of the problems you would have to solve. Now, doing this is very similar to a DC analysis question. So I'm going to go through a DC analysis question of the same format, and hopefully when you see what these similarities are, it will be very easy to go through this problem. So let's say we had a circuit like this, which represents, we have a load here, and the information we have here is the power and the voltage. So we're going to say this is 10 volts, and the power dissipated here, P, is equal to, say, 10 watts. And then I don't know what the resistance is here, just like I don't know the impedance here. And let's just say this is 3 ohms and this is Vs. So I don't have the source voltage here. So you can see it's the same type of information, except now I have just resistive components and DC voltages and currents. So I want to find the source voltage, and I'm not going to bother with the power factor because this is DC, so that doesn't apply. So I want to find the source voltage. So how do I do it? The first thing I could do is find the current. So if I could find this current here, then I could simply add 10 volts to whatever this V line is. So I could say Vs is equal to V line plus 10 volts. So if I know that, then I will know what Vs is. So what is V line? V line is 3 multiplied by I line. So I need to find I line. So I don't have the resistance here, so I can't use V over R, but I do have the power. So I know P is equal to VI, therefore I is equal to P on V, which is 10 watts on 10 volts is 1 amp. And then I know VL is equal to 3 by 1, which is 3 volts. And then I could calculate Vs is equal to VL, which is 3 volts, plus 10 is equal to 13 volts. And that is basically the same thing I'm going to do with the next problem, with our AC analysis problem, except instead of just having P as 10 watts, now I have 50 kilowatts with 0.8 lag. I have an angle to my voltage. I have some reactance here. So it's a complex number problem. But that is basically the only difference. The procedure we go through is the same. In that first we had to determine the current, and we determined the current by looking at the equation for power. Once we have the current, we multiply by the resistance of the line or the impedance of the line to get the voltage, and then I sum them to get the source voltage. So I'm going to do exactly that now, except I'm going to do it with my AC circuit. So I don't have P is equal to VI now. What I have for the AC circuit is S is equal to VI conjugate. And so I have to find VI. So I have I conjugate is equal to S on V. So I need to find I conjugate. I have P here, but I don't have S, so I need to find what this S is first. So I'm just going to do some working on the side here. This is my power triangle. So I know that P is 50 and I have S here. Cosine theta is 0.8. I know the power factor is equal to P on S, which is equal to 50 on S is 0.8. So S, the magnitude of S at least, which is this magnitude here, is the magnitude of S is 50 over 0.8, which is 62.5 kVA. Now I need to find the angle. The angle of S is this angle here. So theta is equal to cosine inverse 0.8, which works out to be 36.87 degrees. So I have, now I could find I conjugate, which is equal to 62.5 angle 36.87 over 440 angle 0, and that works out to be 142 angle minus 36.87. Now this is I conjugate, but I need to find I. So I is simply equal to 142 angle, sorry, this is plus, would be minus 36.87, right? So I found the current. Now, just like I did before, I need to find the voltage across here, VL. So VL is equal to IL multiplied by ZL, which is 142 angle minus 36.87 multiplied by 0.1 plus J 0.05, and that gives me 15.614 minus J 2.8389, which is the same as 15.87 angle minus 10.305. Good. So now I could find VS. VS is equal to VL plus 440 angle 0, and when I add those up I get 455.62 angle minus 0.35. So I've done the first one, find the source voltage. Now I just need to find the source power factor. Now remember, the source power factor is the angle, the cosine of the angle between the apparent power and real power from the source, or the angle between the voltage and current from the source. So what we have so far, if we go back, this 36.87, this is the angle between the apparent power and the real power at the load. It is the load power factor. I need to get the source power factor. So I could go back and multiply VI conjugate and get what is the apparent power at the source, and then get what is the real power at the source. But what I really need to do is I need to get the, or what is the easier thing to do would be to use the voltage and current, because I actually have those angles. I know that the angle on the voltage is minus 0.35, and I know the angle on the current is minus 36.87. So I could say that the source power factor is equal to cosine theta V minus theta I that will be equal to the cosine of minus 0.3571 plus 36.87, and that works out to be 0.804. So that is the source power factor. So I've worked out that, and now I'm going to plot phasors for the source, line, and load voltages. So let me do that here. So first, the load voltage. If I write down the three just to remind you, we have V load, which is equal to 440 angle 0. I have V line, which is 15.87 angle minus 10.3, and I have V source, which is 455.62 angle minus 0.35. So I'm going to draw these out now. So all I do is simply look at the angle and the magnitude. So V load is angle 0, magnitude 440. So this is 440 angle 0. Then V line is 15.87 angle minus 10.3. So I'm going to start from this point, the point where V load stopped, and I get minus 10.3. So that is somewhere around here. So this is 15.87 angle minus 10.3. And those two together, when I add them up, should finish right here. This one should be 455.62 angle minus 0.35. Good. So you'll see here we have a closed triangle. V load plus V line is equal to V source. So that is what we want to see in the phasor diagrams. And that is all the phasor diagrams are. As long as you plot the voltages, as long as you have the magnitude and the angle, you just represent them on the diagram, you put them in on the diagram, and that is it. There is nothing else really to know. The important thing is that you could put only things at the same frequency on the diagram. So I could put voltage, I could put current. I cannot put power, and I cannot put impedance. Sometimes you may see an impedance term in the diagram because you might have IZ, which is actually a voltage. So that does not mean impedance goes on the diagram. Good. So now let's look at the next part of the question. So I did the first two. So I have this one and this one. Now the last part of the question, which is determine the capacitance needed in parallel with the load to correct the power factor to 0.95. So the first thing I have to figure out is how much do I need to correct? How many VARs do I need to correct by? So this is my triangle now. I have 50, 62.5, and this is Q here, and this is equal to the square root of 62.5 squared minus 50 squared, and that it works out to 37.5 kilovars. Now if I had, this is with an angle of 36.87, and remember this angle of 36.87 is cosine inverse of 0.8. Now, which is 36.87. Now I want to correct the power factor to 0.95. So if I correct the power factor to 0.95, then I would have theta nu is equal to cosine inverse 0.95, and that will be 18.2 degrees. So my new, this is the old situation. The new situation is I'm going to have the same real power, because the real power is what is being consumed by the load, and I'm going to have a different apparent power and a different reactive power. Here I'm going to have 18.2 degrees, and now I want to find S and I want to find Q. In fact, I don't really need to find S, I could just find Q, so because that is what I want to correct. So Q here is equal to, Q here will be equal to 50 tan 18.2 degrees, which works out to be 16.43 kilovars. So what I need to do now is I need to subtract 37.5, or I need to subtract 16.43 from 37.5 to find the Q that must be supplied by the capacitor. So I have the Q of the capacitor is equal to Q old minus Q new, and that is equal to 37.5 minus 16.43, which gives us 21.1 kVAR. Now I know that Q is equal to V squared on Z, and the Z for the capacitor, this is V squared on 1 on 2 pi Fc. So that will be equal to V squared, well, let me do it like this, 2 pi Fc V squared. Therefore C is equal to Q over 2 pi F by Z squared, that is 21.1 K over 2 pi F, again F is 60 Hertz, 2 pi F by V squared, 440 squared, and that should work out to be 289 microfarads. So that is how we go about finding the capacitance in parallel. You see that we've combined a lot of the things we did before in the theory, so I hope now with this question it pulls together a lot of what you did. If you're not sure about how to go through it, remember it's just like a DC analysis question in the approach. So if you ever have a question, if you have maybe 2 loads in it, just think about it with 2 loads in a DC system and use the same approach you'd use to find the values of voltage and so on in that case. And of course, for the DC system, you don't have to do things like the phasors and the capacitance and so on, because those things don't apply. Okay, so I hope now you all could see how all of this theory pulls together.